Hey everybody, Doc here. This is our very first lesson. We're in chapter 1. Now, I want to tell you ahead of time that chapter 1 is full of a ton of review. So we go through it pretty quickly. None of it is intended to be anything new that you've learned. So if we hit something in there and you need a little more clarification, please don't be afraid to text or email me so we can go over it a little bit more. Okay, so let's get to it. We're looking at real numbers. We're going to talk about the properties, addition, subtraction, multiplication, division. We'll look at the real line, sets and intervals, absolute value, and distance. Now, we're going to review what kind of numbers are real numbers. So we'll start with the natural numbers. Now, the natural numbers are the counting numbers. 1, 2, 3, 4. You don't start counting with 0, so 0 is not included. So 1, 2, 3, and 4, and etc. No fractions, no decimals. Now, if you add 0 to the counting numbers and then also add their opposites, which are the negative values, then you have the integers. Again, in the integers, there are no fractions or decimals. These are the whole numbers here, which is 0, 1, 2, 3, 4, and then their opposites, and all of that will be considered your integers. Rational numbers are any number that can be written as a fraction. That's what this means right here. It can be written as a fraction. So obviously you cannot have 0 in the denominator. That's not allowed. So some examples are just fractions themselves. We have 1/2, -3/7. But whole numbers and integers and natural numbers are also rational numbers because you can put a 1 underneath them to represent them. A decimal that either repeats or ends is also a rational number. So 0.17 is 1700ths, which means 17/100. Now, there are other real numbers. The real numbers that cannot be expressed as a ratio, such as the square root of 2, is called irrational numbers. Now, you might say, well, can't I put the square root of 2 over 1? Well, you can put the square root of 2 over 1, certainly, or the square root of 2 over any number. However, the square root of 2 itself, when you calculate it, is not a rational number because it is a decimal that has no pattern, it does not repeat, and it does not end. So with that in mind, you can't write it as a fraction because you cannot write the entire number in the numerator. Other numbers that are also irrational numbers are the square root of 3, square root of 5. You see a pattern here. So square roots of prime numbers. Here, the cube root of 2 is also irrational numbers. Sometimes you'll have to just play with it in your calculator to see what's irrational. My favorite irrational number, which is pi. And here we have a whole number that's divided by an irrational number squared. This will also end up being irrational. Now you might notice that it has a fraction bar in it, but again, the number itself, pi, does not repeat, does not end, so it is irrational. So it still is an irrational number. Now the set of all real numbers, denoted by this symbol R, this fancy little R, when we use the word number without qualification, we usually mean real numbers. So unless it is specifically said that the numbers are not real, normally we're talking about real numbers. So here's a diagram to help. This entire area are real numbers. Inside we have rational and irrational numbers. Inside of that, we have integers and natural numbers. I probably would have added one more rectangle in here to just encompass the 0 and the natural numbers and said those were whole numbers, but that's okay. And then finally, we have the irrational numbers on this side. All of these sets are infinite. They go on forever. They don't have an end. There's not a certain number of natural numbers. There's not a certain number of integers. So they're all infinite. And all of them together are the real number system. Good quiz stuff here, by the way. So every real number does have a decimal representation. If it's rational, it will either repeat. Now, they include, if I have 0.5, normally we would not put the zeros on the end, but they're just showing you that you could, so that they could say all rational numbers repeat, which I'm okay with that. And 2/3, we have 0.6666666, so that is 0.6 repeating. This bar means the repeating line. And here we have a decimal that the first number doesn't repeat, but after that, 1717, so you would just put the line over 17. And then here we have a nice long string of numbers that repeat and then repeat again, so you would include everything that repeats underneath that bar. Now, if it's irrational, the number does not have any kind of repeating pattern, and it does not end. So again, the square root of 2 is an irrational number, pi is an irrational number, and several more. Now, we obviously can't write all of the numbers for irrational numbers, so we often do stop at a place, and when we do that, we want to make sure that we don't use a regular equal sign. We want to use this approximation sign, so we can say pi is approximately equal to 3.14159.265. Now we'll look at some properties. Now, in the beginning of your Algebra 1 class, you learned that 2 plus 3 is the same as 3 plus 2, 5 plus 7 is the same as 7 plus 5, and we came up with this property. This is called the commutative property for addition. Commute means to move. So in other words, I could have A plus B, or I could move them around and have B plus A. We have other properties. The commutative property for multiplication also exists. So 3 times 5 is the same as 5 times 3. The associative properties are your grouping properties. I could group these two first, add them, and then add the C, or I could add B and C first, and then add A, and I would get the same thing. It also works for multiplication. Then the distributive property, if you have a value on the outside of the parentheses, you're going to distribute it to each term inside the parentheses. You could also have your single term on the right side of the parentheses, and you would do the same thing. You would distribute it through. So here's an example. If I have 2 times the quantity x plus 3, that would mean 2 times x and 2 times 3. That'll give us 2x plus 6 when we simplify. With that in mind, we often will use this same distributive property to say if I have this entire parentheses, I can distribute it to each term in the other set of parentheses. So if I have a plus b, I'm going to multiply it by x, and then a plus b, multiply it by y. We can use a distributive property here. You may have learned to FOIL, which is fine. You can obviously FOIL your numbers, but this also works, and this method is sometimes handy for when we have a trinomial or a bigger polynomial in the second set of parentheses. Don't really need the parentheses here, so we should drop those parentheses, and then we would say that that is our final simplified form. Okay, let's look at addition and subtraction. All right, now we have a special number, which is 0, which 0 is special because you can add 0 to anything and it does not change the identity of the number, so it's the additive identity. Every number also has its negative, so the opposite of whatever that number is, so negative a. So if you take that number and then you add its opposite, you will get 0. Finally, subtraction can be described as adding a negative. Here are properties of negatives. If we take -1 times a real number, it will be the opposite. A negative of a negative is a positive. These are the same because they all have one negative value and we're multiplying. Again, we have a negative and a negative that will give us a positive. We can distribute negatives, and if we distribute a negative to a subtraction, then we're really just reversing the numbers. Here, if I have a negative on the outside, we can distribute the negative through. If I have a negative times the quantity x plus 2, I can distribute that negative through and then have negative x minus 2. And here I already have the z as a negative in front, so what happens when I distribute the negative? I will get this negative z, which then will become positive. Multiplication and division. The identity for multiplication is 1 because you can multiply anything by 1 and it will not change the value. And every real number has its inverse, which is 1 over that real number, so that when you multiply it by its inverse, you will get 1. And you first learned this probably in algebra when you were solving equations. Division means multiplying by its reciprocal, so that's why we have a divided by b here as being expressed as a times 1 over b. And we can just write a over b as a quotient or as a fraction, and we have the numerator is a and the denominator or the divisor is b. Some more properties here you can see. Now we're starting to look closer at fractions. If we're multiplying, we just multiply the tops and the bottoms. If we divide, we want to multiply by its reciprocal. If we have the same denominator, we can just add the numerators and the denominator stays the same. If we do not, we're going to find a common denominator, and one of the shortcuts to that would just be multiplying the two together. However, you probably know that sometimes that makes things a little more complicated, so that's why you want to find your least common multiple. And here we have our reducing. Okay, my pet peeve. Pet peeves of Dr. Miller right here. This is not being canceled. Cancel means eliminate. I would rather you just cross this out and put reduced. Okay, so we're reducing the c over c as 1, and that leaves us with a over b. We're not canceling it. Canceling means eliminate. We're not eliminating it. It does become a 1. Here, if you have two fractions and an equal sign in the middle, you can cross multiply to begin solving those fractions. All right, so here we go. We want to find the LCD. Now, in order to find the LCD, I do it a little bit differently. I'm going to see if I can use the pen to kind of illustrate. I'm not sure how Well, I'm going to do this, so I'm going to try, actually I'm going to put it up here because I know there will be nothing else that pops up here. So if I have my 36, and I know that my 36 is going to be 2 times 2 times 3 times 3. Sorry about the writing. I'm doing the best I can here. Okay, so that's 2 times 2 and 3 times 3. Now my 120, and the reason I like to show you this is that it works for variables too when we get to those later on. My 120 has 3 2's, so I'm going to put my 2's underneath where the other 2's are already on the top. And I'm going to throw the third one out here on the side because it's extra. And then I have 1 3. And then I have a 5, which isn't included anywhere else. So I'm going to put it over here also. Okay. Put these little dots in indicating that it's multiplication. All right. So now when I want to find my LCD after I spread it out like this, if I bring 1 down from every single column, I have 2, 2, 3, 3, 2, and 5. And once I multiply all of these together, I'll have 4 times 9 times 10. So 4 times 9 is 36, times 10 is 360. Now, what they tell you here is that you look at each one and you take the highest exponents that occur. So the highest exponents will between this one and this one would be, I'm going to have 3 2's. See, that's why I have 3 up here. Between the 3's, I have 2 is the highest exponent, so I have 2 here, and I have 1 5. So whichever way is easier for you, either way, we're going to see that we get 360. Okay, so now that I know that my common denominator is 360. I'm going to multiply my first fraction by 10 over 10 to make it 360, and my second fraction by 3 over 3 to make it 360. Once I do that, now my denominators are the same, and I can add my numerators, and there we go. Went a little fast there, sorry. Okay, so now I have the real line. Now the real line can be called the coordinate line. It can be called the real number line. You will see that different mathematicians like to do this differently. Notice there's no arrow on this end. That's because Stewart, who is the author here, he prefers to look at a number line as going from left to right. So it's showing that it's traveling in a positive direction. This does not mean that it stops here. Okay, there is no solid dot on the end. This just means that it's coming from a negative direction, traveling to a positive direction. This is simply showing that you can plot all of the lines that we were talking about, or all the numbers that we were talking about, whether they are irrational, rational, whole, integers, natural numbers on this line. And we want to use this if the smallest numbers are the ones that are furthest to the left, the larger numbers are the ones that are further to the right. And I often say, think of this as temperature. If I were to write this vertically as a line like this, again, apologize for the crookedness, but if this were a temperature gauge, whatever is the coldest temperatures are going to be smaller than the ones that are the hottest temperatures. Okay, this is what we already discussed. And they're telling you can call this the coordinate line, real number line, or simply just the real line. The real numbers are ordered. We say that A is less than B. Then that would mean B minus A would be a positive number. Equivalently, if B is greater than A, we would write it as B, the symbol greater than A. Okay, so again, here's another line, and they're showing you just the order. This goes smallest to largest. So here I have the number 7. I have 7.4 and 7.5. I would write that as 7 is less than 7.4, which is less than 7.5. Now you'll see we often will read these from inside out. That means I read the number in the middle first. So if I have 7.4 is greater than 7 because I'm reading it this way, and 7.4 is less than 7.5 or 7 5/10. Sets and intervals. Okay, we're going to take a look at set notation. Set notation is a collection of objects. They are indicated by uppercase letters. And we use this symbol right here, which is called the element of. So we would say A is an element of set S for right here. If you put a line through the element of symbol, that means not an element of. So, for example, if Z represents the set of integers, then -3 is an element of Z. But pi is not an element of Z because pi is not an integer. Some sets can be described by listing their elements. For instance, we might want to use A equals and embraces, list the actual elements that are included in that. And we also, whoop, I think we went backwards one. We also can take a look at set notation. So let's take a look at that. The set notation, I'm going to go ahead and look at it. I think it comes up on the next slide, so I'll introduce it then. So now this would mean that we would intersect two sets, and this means that we would take everything that is in S and in T, meaning it has to be in both. So if it's not in both sets, then we say it's an empty set and contains no elements. All right, so let's practice this. So this is a union symbol here. We skipped over that slide a little bit. So this is a union symbol. This means that it would be in S or in T. So whatever's in S or T, we would include them all. This is the intersection symbol, which means it has to be in both. And this is another intersection symbol, which also means in both. Here we have three sets. We have S, 1 through 5, T, 4 through 7, and V, 6, 7, 8. And these are all whole numbers. So if we want to find the union of S and T, we're going to combine the two of them. So I would take everything in S and then whatever else is in T that wasn't also in S, and I would list them. So that would be my union. And my intersection means what is both in S and in T. So here I have my 4 and my 5 that are in S, my 4 and 5 that are in T. They're in both, so there you go. And if I want to intersect S and V, I want to see what is the same in S, what is the same in V. I see nothing that is in both, so that would be the empty set symbol. Now, we can also use interval notation. So intervals occur a lot in calculus. So we're going to take a look at if A is less than B, then we would have an open interval from A to B to consist of the numbers between A and B, but not including A and B. Okay, so anytime I have these parentheses here like this, that means everything in between A and B. Again, this is interval notation. This is not a coordinate. This is interval notation. Now, if it's a closed interval, meaning that it would include A and B, then we're going to use these square brackets here to say that we want to include the A and the B. Set builder notation. I want to talk a little bit about this. So this first variable just means the variable that we're going to use here. So this is interval notation from A to B, but not including A and B. It would be X. This line means such that A is less than X and X is less than B. However, we usually read this from inside out. So we're going to say that A is greater than, or X, I'm sorry, X is greater than A and X is less than B. Notice the difference. If I have the square brackets here, I'm including them. So I have X such that X is greater than or equal to A, including the A, or X is less than or equal to B. Okay, here's the difference on a number line. We would have the open circles. If I have the parentheses, which shows that it does not include A and B, and if I use the solid brackets, the square brackets, then I'm going to have the closed filled in circles, which means I do include A and B. Right here, I'm going to tell you, this is good quiz stuff right here. Okay, so this is the notation. This means everything in between A and B, written like this. Notice there are no lines under the inequality signs because it does not include A and B. So this is X such that X is greater than A and less than B. Both of those are open circles because it does not, again, include A and B. Whenever it does include A and B, you'll notice the difference. We now have the lines underneath the inequality signs because we do now include A and B. It can be mixed together. The first one might be included, the second one may not. Then we would have a square bracket and then a parenthesis on the end, and that would look like this on the number line. If I want to not include A, but I want to include B, again, I would put the inequality, the line under the inequality symbol saying or equal to, and that will include my B value. Now, I could take a number to infinity. Infinity is always what we call unbounded. We always use a parenthesis. That's because it does not have an end. So you always use a parenthesis and not a square bracket. So here this would look like this because we're not including A. And then the next one, if I start with a square bracket, I am including A. I have right here, and both of them going to infinity. I can also do from negative infinity to B, open circle because I'm not including B, closed circle when I am including B. And then if I go for the all real numbers, I would have negative infinity to positive infinity, both in parentheses because we do not have an end to infinity, and we would color in the entire line. Okay, so if I were to graph each set, now this is how I like to do this. Let's take a look. I'm going to try to put it where I won't be in the way. So if I take the pen and I want to do 1 to 3. So I'm going to draw a number line here, try to keep it straight, and of course I didn't. So now I have the numbers 1, 2, 3, and 7 on here. So that means I'm going to start here with 1, and we'll just do 2, 3, 4, 5, 6, and 7. So I have my open circle on my 1 value. Again, this starts with 1 and it goes to 7. Okay, so I have 1 to 3. So 1, 2, 3. right here, both open circle. Now I'm going to change up the color a little bit so that I can use green in between. So here we have that. So that would be this part. And then the next part would be including 2 through 7. I'll use yellow. And I have the 2 here, close circle for 2. And to 7. Also close circle here. Now, the question in this problem is, what is the intersection? So I'm saying, what is the same in both? So that would mean, where is the overlap? So it looks like I have an overlap at 1, including 1, or no, 2, I'm sorry, this is 2, 1's over here. 2 and including 2, but not including 3. So I would write that as including 2. And I'm going to go to 3, but I'm not including 3. And I put my parenthesis right here. Okay, so this is the way I like to do it. And let's take a look at how they do it. So the intersection consists of numbers that are in both intervals. And here we have, this is just describing what each one of those was. Greater than 1, less than 3, greater than or equal to 2, less than or equal to 7. And we see that what is in both is 2 and including 2 and not including 3. Now here they show you exactly what I did, but in 3 separate lines. And there again, we're looking at the overlap. This is included in both, and it would go in 2, but not including 3. So here it is there. Now the union means you want to have the numbers that are in one or the other, or both. So here I'm going to take a look at the same number line that I did before. And I see that I'm going to start at the 1 and I'm going to go clear through to the 7 because I'm including everything. I'm putting everything together. So this is the lacrosse team and this is the library club, and we're putting them both together to go on a field trip. The library club is going to be doing a news article on the lacrosse team. So we would have not including 1 because it's not included, 2 and less than or equal to 7, and this would be my final answer here. You can also use the number lines to take a look at that as well. You want to see where do you start, where do you end, and include them all. Now if there's a gap in between here where they're not in either one, you would not include that. Okay, absolute value and distance. Absolute value and distance. So anytime you have an absolute value, what you're looking at is the distance from 0. So here we have the absolute value of -3 is the distance from 0 to -3, and we get 3. And then we have absolute value of 5 is 5. Now this is kind of this is a definition of the absolute value. A lot of people find it confusing. This just means if the number on the inside is already a positive number, then that's your answer to your absolute value. However, if it is a negative number on the inside, then it's going to be the opposite of that negative number there. Okay, so we have the absolute value of 3 is 3. Absolute value of -3 would be the opposite of -3, which also is 3. Absolute value of 0 is no distance. And the absolute value of 3 minus pi, because pi is a number that is bigger than 3, would be the opposite of 3 minus pi. And we would just reverse them because you would distribute your negative, and it would be pi minus 3. So there's some properties of absolute values, what we already discussed, except for probably here is the multiplication. You could take the absolute value of A and the absolute value of B first and then multiply. It's the same. Here's the division. You could take the absolute value of the whole thing, or you could just do the top and the bottom. All right, if this is the distance between the points A and B, can be asked if you have the lowercase d in front of your interval. You would take your furthest one, which is B, and subtract A. That will give you the distance from A to B. And again, A and B are in numerical order, with A being the smallest and B being the largest. So if I'm looking at the distance from -8 to 2, I would take that -8 minus 2 absolute value. I would have -10, and the absolute value of -10 is 10. If we look at that on a number line, we see that our distance from -8 to 2 would be 10 units. Okay, that was our last slide. And this is a lot of information in one section, but again, it's supposed to be review. So hopefully it was a good review for you. And if you have any questions, you can always text or email me.